So section 6.4 will discuss unsaturated hydrocarbons, both alkenes and alkynes. Alkenes are unsaturated hydrocarbons with one or more carbon-carbon double bonds. And they have one or more carbon-carbon multiple bonds. That's an unsaturated hydrocarbon. Alkenes with two double bonds are called dienes. Alkenes with many double bonds are called polyenes. An example of a polyene is beta-carotene, shown here in the skeletal line drawing. We can see the double bonds as two parallel lines, and you can notice that there are many double bonds in beta-carotene. This is incidentally a good source of vitamin A. So the parallel lines here again denote double bonds between the carbons, and so if we look at this carbon right here, we notice that it has three bonds to it already, two to the double bond to the left, single bond to the right. So that means it only has one hydrogen pointing down that we can draw in with our mind if we want to, or on a paper we could draw in this hydrogen if we needed to observe more detail about it. So let's look at this practice problem here. Here's the structure of vitamin A, or retinol. How many double bonds does vitamin A contain? Well, again, this is the skeletal line structure, so we look at the parallel lines to find double bonds. There's 1, 2, 3, 4, 5. There are 5 double bonds. In what way does it resemble beta-carotene? Well, it is a polyene, and it's essentially half of beta-carotene. If we go back to beta-carotene, remember that there is a six-membered ring on the left side of vitamin A, several methyl branches, right? These are methyl branches. And if we go back, we see that we have methyl branches, a six-membered ring with some branches here, and the same thing reversed on the right side. So beta-carotene, if we can split it in half, we get to vitamin A. So the next question, how many carbon atoms have 3 hydrogen atoms attached to it? Well, a carbon atom that will have 3 hydrogen atoms will be the end of a line. So this is a carbon atom with 3 hydrogens attached, and we can fill that in if we want to. Same with this one, and this one, and that one. So there are 5 carbon atoms that have 3 hydrogen attached. How many carbon atoms don't have any hydrogen atoms? So now we need to look at carbons that have 4 bonds to them already without drawing in any additional hydrogens. I think we'll see one right here. It has 2 single bonds, 2 double bonds. Same with this one, 2 single bonds, 2 double bonds. This carbon here also has 2 single bonds and 2 double bonds. And same with this carbon as well, 2 single bonds, 2 double bonds. So there's 4 right there, and we have one more, a 5th one right here, that has 4 single bonds already drawn in it. So the answer to this is also 5. There are 5 carbon atoms that have no attached hydrogen atoms. Vitamin A is not specifically classified as a hydrocarbon. Why? Well, it has an OH group. So right here, it has an OH group. That makes it not technically a hydrocarbon. We can say that the rest of the molecule here is a hydrocarbon. It has hydrocarbon character because there's only C's and H's. But technically, the entire retinol is not a hydrocarbon. Would we consider it to be hydrophobic or hydrophilic? And the hint says vitamin A is one of the 4 fat-soluble vitamins. Fats are made of nonpolar molecules, so oily, and so we would expect it to be hydrophobic or water-fearing. And some of you might say, well, it has an OH group here, so shouldn't it be hydrophilic? It's polar, has hydrogen bonding capability, but there are too many carbons in order to dissolve this in water. There's just too much nonpolar character on the left side of the molecule. There's only one OH group, and so that's not strong enough. It's not polar enough to bring all the rest of this hydrocarbon structure into water. So it's not polar enough to dissolve in water. Clicker question 6.5. How many carbons have 1 hydrogen attached in this line drawing? And so I think if we think back, These carbons at the end of lines have 3 hydrogens attached, so it's not any of those. These carbons here have 3 lines going to them, and so they only need 1 more hydrogen to be attached to them to have 4 bonds. So I think this carbon has 1 hydrogen attached. This carbon has 1 hydrogen attached. This one has 2. It has 2 lines, needs 2 more. So the best answer here, B, is 2. 1, 2. So now we want to define a topic called geometric isomers. And so, unlike a carbon-carbon single bond, there's no rotation around a C-C double bond. So the alkenes are locked in a conformation, and this leads to geometric isomers, compounds with the same chemical formula and the same connectivity of atoms, but they have a different 3D orientation. And that can only happen around a carbon-carbon double bond. And they are going to have different chemical and physical properties. They don't exist for alkanes because alkanes have only single bonds, and those allow for free rotation. So some examples of geometric isomers. So here's a 4-carbon alkene. It can exist as these 2 geometric isomers. The cis isomer, where if we draw a line through and parallel to the double bond, we see the methyl groups, or the carbon groups, are above that line. They're on the same side of that line. It's called the cis isomer. A line through and parallel to the double bond has the methyl groups on opposite sides. That's called the trans isomer. And we call these the heavy groups because they are heavier than a hydrogen. CH3 weighs more than a single hydrogen. So heavy groups on one side, cis isomer. Heavy groups on opposite sides of that double bond, trans isomer. And these are geometric isomers because we cannot rotate around this double bond, and so they can't easily interconvert. So these are 2 different isomers of this 4-carbon alkene. So we have 2 methyl groups attached. They occupy different regions in space. This one is the same. They're both in the up position, but in the cis isomer, this rightmost methyl group is up. This rightmost or methyl group in the trans isomer is down. They occupy different regions in space. So let's draw some geometric isomers, get some practice with that. We want to draw the geometric isomer for the following compounds and indicate whether the isomer shown is cis or trans. So first off, let's look at this one. There are 5 carbons in a row, 1, 2, 3, 4, 5. We can draw the isomer by moving one of these groups to the opposite side. So we can draw C's, we can draw that C, and now instead of going up, we'll just go down. And then we'll add hydrogens as appropriate. This carbon has 3 bonds to it, so it needs only 1 more hydrogen. This carbon has 3 bonds to it, needs only 1 more hydrogen. And so this is the trans isomer. How do we know that? Well, drawing a line through and parallel to the double bond, we see the heavy groups, in this case, are both up. So this is cis. They're both on the same side of that line. If we draw the line here, heavy groups are on opposite sides of that line, so they are trans. In this drawing, the heavy groups are this methyl group and this 3-carbon group. They are on opposite sides, so they are trans. And so we can draw the cis isomer very easily. Here's the double bond, 1, 2, 3, the 3-carbon group down to the left. Excuse me. The methyl group now on the right is up. If we want to draw the opposite isomer, we draw it down. Now this is the cis isomer, right? Both heavy groups are on the same side of an imaginary line through and parallel to that double bond. So trans and cis. Alkynes are unsaturated hydrocarbons that contain 1 or more triple bonds between carbons. The symbol of these alkynes is called ethyne or acetylene. It's often used in welding. It has 2 carbons, 2 hydrogens, and a triple bond between the carbons. And this, of course, has linear geometry because the carbons have only 2 bonding groups, and 1 on either side gives it a linear geometry. So the entire alkyne is linear. And geometric isomers don't exist for alkynes. We can't have any other arrangement of these carbons. They have to be in this same arrangement. And they're not really common in nature. Here's one example. strionicotoxin, it has two alkynes here on these ends of these chains. So alkynes do exist in nature, but they're not very common.